So from patterns with addition, we have patterns with subtraction. And so here on this activity, we're going to add on those patterns of addition. So this first one makes pretty good sense, right? We start off with things that they know, -4 minus 1, -4 minus 2, and then it leads into the negative numbers here. How could we justify starting with the 3 minus 4 and the 2 minus 4? Right, because with patterns, you got to start with something people know so that they can continue it. Like the first part, oh yeah, that makes sense. Now I can continue it. Oh, if the first part made sense, the rest of it's got to be true. Right, that's kind of the gist of patterns. So how could we justify the 3 minus 4 up there? We could have done an addition problem, right? That says, yeah, it's 3 plus -4, so that's one way to do it. Okay, and we talked about addition before, so okay, we get that as a -1. Is there another way we could kind of explain the 3 minus 4 is -1? Switching over to this pattern over here. Right, because we got the 4 on the other side, right? Notice the difference between these two tables? We flip the 4 to the other side of the subtraction. What happens when we change the direction of subtraction? 4 minus 2 versus 2 minus 4. It flips the sign. Yeah, that's what we're doing here, right? And that's one thing we can demonstrate to get this started. Watch, when we change the direction of subtraction, we change the sign of the answer. We bring it to the other side of the number line. Yeah. So that's another tool we could use to kind of get this table going, and then the kids can continue it from there. So it's all a matter of getting them comfortable at the beginning of the pattern, and then they see how to finish it, to get used to why -3 minus 4 should be -7. Or down in this table, -4 minus -2 is -2. Okay, so for some more complicated facts, like this table 3 over 4 and 2 and 4, those are pretty complicated because we're subtracting negatives. We have negatives on both sides at sometimes. So sometimes there's a little bit of work to do before you can even set up the pattern, start working with it. But patterns can be a pretty powerful tool. So let's jump and take a look at patterns for multiplication. So we can do a similar thing with multiplication. We can do the same thing with division too. So patterns are another way to model stuff. So we're pretty comfortable with 4 times 3 is 12, and 4 times 2 is 8, and 4 times 1 is 4. 3, 2, 1, the next obvious number we want to put down is 0. And we know 4 times 0 is 0. And then we're developing a new pattern over here on this side. Right? 3, 2, 1, 0 is pretty straightforward. How could we describe the pattern that we're developing on the other side of the equals there? 12, 8, 4, 0. What's the pattern to that sequence? Yeah, it's taking away, subtracting, dropping by 4 each time. And so if we drop 4 from 0, where are we going to end up? Yeah, -4, and then at -8, and then -12. And -16. And so that tells us on this side, if we take 4 times -1, that ought to be -4. We take 4 times -2 as the next obvious number, it should be -8. We'll talk about that with chips in a minute too. 4 times -3 should be -12. 4 times -4 should be -16. Oops, I'm missing the 1 on that 16. So we do a similar pattern for number 2 once we fill that out. And then we try to get a rule out of that. Does this lead to any conclusions that we can make based on the numbers we multiplied and the answers? Does that tell us anything? Are we seeing a continued pattern from when we multiply a positive times a negative? Yeah, what are the kids going to say? If we take a positive times a negative, the answer looks like it's going to be negative, right? I'm answering that next question there. And the next table helps to reinforce that. 4, 3, 2, 1, 0, -1, -2, -3. So this side was a positive times a negative. Now we get to try our hand at a negative times a positive. Does it matter the order that we multiply? Now, there's already a good sense that it doesn't matter, but you can't take anything for granted. We've got that pattern down this side we have to develop. 20, 15, 10, how would I describe the pattern to continue it? Drop by 5, so 10, we would drop to 5, and then 0, and then to -5, right? We're getting used to that number line with negative numbers. Yeah, so then we can develop this rule that, hey, it looks like if we multiply a negative times a positive or a positive times a negative, the answer is still negative. Otherwise, aren't we just multiplying like usual? So we're developing an algorithm. So the algorithm is kind of the rule. What happens when you multiply numbers of a certain kind of sign? Now, once we have that established, we can jump down to some more complicated ones. So we come down to parts 4 and 5 here. We have the -3's coming down here. 2, 1, 0, -1, -2, -3, -4. We know a negative times a positive is a negative, and 3 times 1 is 3. We know anything times 0 is 0. So how would I describe this new pattern here? Oops.
3.
We're adding 3. Yeah, the numbers are increasing this time. We're heading towards 0, and then we're going to move past it. 3, oops, back. 3, 6, 9, 12. And we start to see, oh, look at this. A negative times a positive is a negative, but what, can we develop a rule now for a negative times a negative? Yeah, it looks like it's a positive, and we're going to need to do more examples. Just a few isn't enough. So right away, with the pattern here, we get into an algorithm for how to multiply integers. And really, we already know how to multiply. It's what do we do with the signs is the big thing. And the pattern is a nice way to get at that. All right, let's finish this table off, and then we'll look at the chips for doing multiplication. Multiplication with chips or charged particles. So what were some of our models for multiplication before, when we were just doing whole numbers?
Groups of?
Yeah, groups of, and that's the best one to use here. You kind of get away with the array. The area doesn't work out so well, but it can. Groups of. So multiplication means groups of. Right, so for example, we know 6 times 3 is 6 groups of 3. Okay, so there's my 6 groups of 3. I count them up and I get 18. Now, I could throw in the idea of integers, where this is a positive, and this is a negative, and this is 0. So if I add that model here, then what have I actually drawn a picture of above? Yeah, I actually just drew a picture of 6 times -3, which is 6 groups of -3, which has to be, count them up, there's 18 of them, they're all negative, so it has to be -18. Okay, so that works pretty good. Just like the addition before, I have a bunch of things with the same sign I have to add up, so they stay the same sign. The tricky part is, can I model something like -2 times -3? So this is something I'm going to do early on before they know the rule that a negative times a negative is a positive. We need to try and develop that rule. Okay. So if we didn't use the patterns, maybe we're going to use the chips. So let's see. Difference here is I have to figure out, what do I do with this negative right there? This one's not a problem. We just dealt with that in the other one. That was easy. The negative in front's a problem. Over here, that was a +6, so I just put down 6 groups of -3. Before I drew those 6 groups of -3, would you agree there was nothing there? So we had to start with nothing and then throw down 6 groups of -3. So what's one of our interpretations? We have a lot of interpretations for negative signs. Okay. One of them's opposite. Opposite's a tough thing to deal with. It means go to the other side of the number line. But another one is take away, right? So is it possible that this could mean take away 2 groups of -3? Let's give it a shot, see what happens. So in the previous problem, I started with nothing and I threw down 6 groups of -3. Here, I'm starting with nothing, but I got to take away 2 groups of -3. How can I take something away from nothing? Do we have a trick for that? Yeah, zeros. We have this clever trick where, hey, here's nothing, that's a 0, and here's another 0, and here's another 0. Do I have 2 groups of -3 yet? No, I got 1 group of -3, so I just put in some more zeros. So the trick here, 2 things. One, we interpret the first negative as take away, then use zeros to build what we want to take away. And we're already used to building because we did it with subtraction. So I just build a few more of these. So now I can take the the 2 groups of -3. So I'm taking that, and that, and that. There's 1 group, that, and that, and that. That leaves what? +6. So we can do it. Not too bad. So if I was presented with a slightly different version of the 2 problems we just looked at, say -2 times 3, I have a couple of options. I could throw in a bunch of zeros and then take away 2 groups of 3. Or we've already developed the rule that it doesn't matter the order you multiply in. I could rewrite this as 3 times -2. And then it's a little easier that way. We have a couple of options on this one. So there's ways to model it. You got to get used to the models, and then the models allow you to get used to the rules. And the rules we have are that if you multiply numbers of the same sign, it's positive, right? If you multiply numbers of different sign, it's negative, right? Let's write that down. Rules for multiplication of integers. Multiply by same sign for a positive answer. Multiply by different sign for negative answer. So that's our algorithm for multiplication of integers. So we're going to backtrack a little bit, and then we're going to do a little algebra with signed numbers, and then we're almost done with this stuff. So we came up with a couple of definitions of what opposite means. So I just want to go over that and then show you a little algebra with signed numbers. So a couple of versions of opposite. One was if you have an opposite and you add it, you get 0, right? It's the number you add to get 0. So that was one version. Another version was the number line version of opposite. Opposite side of the number line, an opposite side of 0, but same distance. And the other version was the more algebraic way to look at it. This symbol means opposite. So the opposite of 6 means -1 times 6. The opposite of -2 means -1 times -2, right? That symbol for the opposite just means multiply by -1. That's the way computers think about it. So I'm going to kind of combine 1 and 2 just to talk more about multiplying two negative numbers. So the big question with multiplying integers essentially boils down to what is -1 times -1. Because once we answer that, we know what opposite means, then everything else kind of falls into place. So we'll go to this first. We know that 1 plus -1 is 0, right? That's one idea of opposite with 1. We also know from algebra, it's okay if we multiply the same number on each side. So what I want to do is I want to take this equation, 1 plus -1 equals 0, and I want to multiply both sides by -1. So the right side's pretty straightforward. What do we get on the right? Do 0. The left side, well, what happens here? I have -1 times 1 I have to distribute, right? And what happens when I multiply by 1? Yeah, multiplying by 1, the number you multiply by doesn't change, so we're definitely going to have a -1 here. And then we're going to have -1 times -1 when we distribute there. Yeah, and one way to answer this question is using this little bit of algebra here. What could -1 times -1 possibly be so that this equation stays true? And the only option is what Tiffany says, it's got to be 1. Otherwise, we can't do this, or maybe this is false. But I know this is true, and I know that's true. Now, I'm not going to do this with kids. I'm just doing it with you guys because you're adults and you've done algebra before. But just taking this little idea from algebra that we can multiply the same number on each side, we can then use that to come to the conclusion that, hey, this has got to be 1. And that's kind of like the fundamental thing that makes multiplication of integers work. All right, almost done. Division. Is division much different with integers than multiplication? So we got to figure out, now we're already really good at doing problems like 12 divided by 3. That's no big deal. But now we have to do things like 12 divided by -3, or -12 divided by 3, or -12, oops, this was 12. Divided by -3. And so I think the easiest way to come about this is to use the missing factor model. So with the missing factor model, we would say, okay, this equals what? And then we would pretty much write it backwards. What times 3 is 12. So we could rewrite each of these. What times -3 is 12. What times 3 is -12. And what times -3 is -12. So we already have rules for multiplication, right? Multiplication, we know that to get a positive, I have to multiply two numbers of the same sign. Now, we already know that 4 times 3 is 12, so this answer here has to have a 4 in it. The question is it +4 or -4? What's it got to be here?
Or the first one?
The second one. Yeah, sorry, the first one is just, sorry. The first one's just stuff we already know. Yeah, and the second one is going to have to be a -4, because a negative times a negative is what we need to be a positive. The second one, we have a negative answer. We have a positive number here. What do I have to multiply by to get a negative answer? So this one has to be negative also. Here, I've got a negative answer and a negative number. What can I multiply by to get that negative answer? That one would have to be positive, right, from the rules that we've already developed. So based on these examples, can we come up with new rules for dealing with? We already know how to deal with multiplication. What are the rules for division?
They're essentially the same.
They're the same rules, yeah. There's no difference, really. Otherwise, you're going to have to know how to divide, but determining the sign. So the rules if the numbers are the same sign, you get a positive answer. If the numbers are opposite in sign, and you'll get a negative answer, which is identical to the rules for multiplication for determining the sign. Otherwise, it's just division as usual. Not too bad. And I think we are almost done with my numbers. All right. Activities we need to get done. 1, 2, 3, 4, 5, and 6. And we've talked a little about each of those now, I think. We just need to get them done. All right. So I'm going to stop here